Welcome to our first lecture in Physical Chemistry 3 Spectroscopy. In this course, we'll explore one of the most fascinating bridges between physics and chemistry, how light interacts with matter. Spectroscopy is not just a set of tools, it's a language. It's a language through which atoms and molecules speak to us, revealing their internal structure, their motions, and even their hidden dynamics. No matter which research field you choose, you will find spectroscopy playing a role there. Today, we'll start with a broad overview what spectroscopy is, how it was developed historically, and the fundamental physical principles behind it. In this course, we'll cover 6 sections. We'll begin with the fundamentals of spectroscopy and then move on to rotational, vibrational, Raman, optical, and NMR spectroscopy. To guide you, I recommend 4 books: Banwell for a clear introduction to molecular spectroscopy, Mech-Haller for deeper theoretical insights, especially time-dependent quantum mechanics, Pavia for real-world examples and problem solving, Atkins for the physical chemistry foundation, and obviously you don't need to read all of them to cover the syllabus, but together they provide theory, exercise, and applications. I have used these books to prepare this current lecture. With our first lecture, I want to talk about firstly the key learning points. Here are the 4 big questions we'll focus on today. What is spectroscopy? What are the different techniques and what do they tell us? How does radiation interact with matter? How do we connect the electromagnetic spectrum with quantized energy levels in molecules? By end of today's lecture, you should already have a clear sense of these ideas. Spectroscopy. What is spectroscopy? Spectroscopy is the study of how electromagnetic radiation interacts with matter. That might sound abstract, so let's break it down. We shine light, or more broadly, radiation, on matter. The matter responds, it absorbs, it emits, it scatters. By analyzing that response, we learn about structure and properties at the atomic and molecular level. In short, spectroscopy is how we use light to make the invisible world visible. Even the word tells the story. Spectrum comes from the Latin appearance. Scopian in Greek means to look at. So spectroscopy literally means looking at appearances with light. To appreciate spectroscopy, we need to see where it began. Imagine the year 1666. Isaac Newton darkens his room, makes a small hole in the window shutter, and lets a narrow beam of sunlight in. He places a prism in its path, and suddenly the white light burst into a rainbow of colors across the wall. This was revolutionary. Until then, most people believed that white light was pure and that the prism somehow created the colors. Newton showed the opposite. White light is actually made up of many colors with its own character. For the first time, humans realized that light itself has an internal structure, and that we can study it by breaking into components. From this simple prism experiment, spectroscopy was born. Fast forward about 150 years to the early 19th century. Joseph von Fraunhofer, a German optician, was studying the sun's spectrum. With much better instruments than Newton had, he noticed something strange. The rainbow of sunlight wasn't perfectly smooth. It was interrupted by thin, dark lines, hundreds of them. What did they mean? At the time, no one knew. Later, these lines were linked to atoms in the sun's atmosphere, absorbing specific wavelengths of light. Fraunhofer didn't know the quantum explanation, but he gave us a powerful tool, the precise measurement of spectra. Those black lines were the fingerprints of atoms. This was the first connection between light and internal structure of matter. Now let's jump to the late 19th and early 20th century. Physicists kept noticing that classical physics couldn't explain many spectroscopic results. Why should atoms only absorb or emit certain colors instead of a continuous rainbow? The answer came with the quantum revolution. Energy is quantized. Atoms and molecules can occupy only discrete energy levels, and light interacts with them only when its energy matches the gap between those levels. Niels Bohr's model of the hydrogen atom captured this beautifully. He pictured electrons in orbits, each orbit corresponding to a quantized energy. When an electron jumped from one orbit to another, it absorbed or emitted a photon of exactly the right energy. It wasn't yet the full modern quantum mechanics, but it explained why Fraunhofer saw sharp lines and why Newton's rainbow contained hidden structure. Spectroscopy was now directly linked to the birth of quantum theory. Meanwhile, what is light itself? In 1801, Thomas Young performed his famous double slit experiment. He passed light through two tiny slits, and instead of two bright spots, he saw an interference pattern, alternating bright and dark fringes. This was only possible if light behaved as a wave. The waves from the two slits overlapped, sometimes reinforcing each other, giving bright bands, sometimes cancelling, giving dark bands. If light were only particles, you would simply see two bright dots. A good way to picture this is with water waves. Imagine dropping two stones into a pond. Each stone creates a ripple that spreads out. Where the ripples meet, sometimes the crests add up to make a higher wave. That's constructive interference. Other times, a crest from one meets a trough from other, and they cancel. That's a destructive interference. The spacing between ripples is the wavelength. Young's experiment was crucial. It showed that light has a wave nature. This wave picture explained refraction, diffraction, and interference. But science is rarely so simple. In 1905, Albert Einstein turned the picture upside down with the photoelectric effect. Imagine shining light on a clean metal surface. If the light's frequency is high enough, electrons are ejected from the metal. But if the frequency is too low, no electrons come out, no matter how bright the light is. Classical wave theory couldn't explain this. According to it, making the light more intense should always knock electrons out, regardless of color. But experiments showed the opposite. Frequency, not brightness, was the key. Einstein explained it by saying that light is not just a wave. It comes in discrete packets of energy called photons. Each photon has energy E is equals to h nu, where h is Planck's constant and nu is frequency. Only photons with enough energy can knock electrons free. Brightness simply means more photons. But if each photon is too weak, nothing happens. Think of it like throwing balls at a wall. A handful of ping pong balls, no matter how many you throw, will never break it. But a single fast baseball might. For this idea, Einstein received the Nobel Prize in 1921. It proved that light also has a particle nature. So, what is light then? A wave? A particle? The answer is both. When light travels, spreads out, and interferes, it behaves like a wave. When it interacts with atoms and molecules, when it is absorbed, emitted, or when it knocks electron out of the surface, it behaves like a particle. This is what we call wave-particle duality. Wave language is wavelength, frequency, interference. Particle language is photons with energy E is equals to h nu. And this isn't just philosophy. In spectroscopy, we actively use both models. Sometimes we treat light as a wave, sometimes as photons. It depends on the experiment. That duality is at the very heart of spectroscopy. To truly listen to atoms and molecules, we need to be fluent in both languages of light. Now let's bring this back. Let's bring this back to spectroscopy. Different spectroscopic techniques emphasize different aspects of light. Infrared spectroscopy, mainly wave-like, the oscillating electric field couples with molecular vibrations, so we describe it in terms of frequency and wavelength. Raman spectroscopy needs both. The photon view explains inelastic scattering, but the wave view is essential for polarization and interference. UV visible absorption, again both. Photons excite electrons to higher level, but wave properties shape the intensity and width of the absorption bands. X-ray photon electron spectroscopy, purely particle-like. Photons eject electrons and quantized energies are the key. X-ray diffraction, purely wave-like interference patterns come from waves diffracting through a crystal lattice. NMR spectroscopy, both again, the photons are quantized, but resonance and signal analysis rely strongly on wave behavior. So you see, spectroscopy forces us to be bilingual, fluent in both the wave language and the particle language of light. Until now, we have only spoken about light. But in 1924, Louis de Broglie made a revolutionary suggestion. What if matter also has wave-like properties? He proposed that any particle with momentum p has an associated wavelength given by the formula lambda is equals to h by p, or in words, where lambda equals h divided by p, where h is Planck's constant, and p is the momentum of the particle. This means not only photons but also electrons, atoms, even baseballs, in principle have wave-like character. Of course, for everyday objects, the wavelength is unimaginably small, so we don't notice it. But for electrons, the wavelength is comparable to atomic dimensions. That's why electron diffraction works and why quantum mechanics is essential. This duality of matter is absolutely crucial for spectroscopy. It explains how quantized energy levels forms in atoms and molecules as standing waves of matter, and it explains how photons as particles can interact with these quantized matter waves. In short, spectroscopy rests on the wave-particle duality of both light and matter. Let's pause for a quick check of understanding. You can read the question, and each question I will wait for about few seconds. You can pause this video and look for the answer, and then the answer will appear. What is the primary definition of spectroscopy? The study of how electromagnetic radiations both shows wave and particle behavior, the investigation of the interaction of electromagnetic radiation with matter, the determination of molecular structures and quantized energy levels, the application of light for compound identification and medical imaging, Okay, so let's wait for around 40 seconds and then I will give the answer. The answer is B. Spectroscopy is the investigation of interaction of electromagnetic radiation with matter, and that's the foundation of this entire course. Next question is, which historical figure demonstrated that white light is made up of different colors using a prism experiment? Joseph von Fraunhofer, Albert Einstein, Isaac Newton, Louis de Broglie. And the answer is Isaac Newton. Back in 1666, by passing sunlight through a prism, he showed that white light contains all the colors of the rainbow. And this experiment was the beginning of spectroscopy as method. Next question is, Joseph von Fraunhofer is renowned for his discovery in the early 19th century of what phenomenon related to light? The photoelectric effect, dark lines in the solar spectrum, later linked to atomic absorption, the wave nature of light demonstrated by interference patterns, the quantization of energy in atoms. The correct answer is B. In the early 19th century, Fraunhofer observed dark lines in the sun's spectrum. Later, these were shown to come from atoms in the sun's atmosphere and selectively absorbed certain wavelengths. Fraunhofer's careful measurements gave spectroscopy its precision. Even though he didn't know about quantum theory, his work laid the foundation for linking spectral lines with atomic structures. Next question is, in 1801, Young's double-slit experiment provided key evidence for which property of light? Light's ability to exert pressure, light's particulate nature, consisting of photons, light's wave-like behavior demonstrated by interference patterns, light's constant speed in a vacuum. And the correct answer is C, light's wave behavior. Those alternating bright and dark fringes could only be explained by waves interfering. If light were just particles, we would have seen only two bright spots, not that delicate pattern. Young's experiment is still one of the most elegant demonstrations of the wave nature of light. Next one. Albert Einstein's explanation of the photoelectric effect provided crucial evidence for which property of light? Light's ability to bend around obstacles, light's wave-like behavior as it spreads out, light's particulate nature, where it consists of energy packets called photons, light's ability to be refracted when passing through different media. And the answer is obviously the particle nature of light. Light comes in discrete energy particle packets called photons. Only photons with enough energy can reject electrons from a metal. This duality is exactly why spectroscopy works. Sometimes we describe light as a continuous wave, sometimes as a stream of photons, depending on the interaction we are studying. How does spectroscopy generally utilize the wave particle duality of light? A. It uses both models to understand how electromagnetic radiation interacts with matter. It exclusively relies on the wave model for all interaction. It exclusively relies on the particle model for all interactions. It considers light only as a particle when it propagates and as a wave when it interacts with atom. The correct answer is spectroscopy uses both models to understand how electromagnetic radiation interacts with matter. Next question is, de Broglie's revolutionary idea, which is crucial in spectroscopy, stated that only light exhibits wave-particle duality. The speed of light is the maximum possible speed in the universe. Energy can be converted into mass and vice versa. Not only light, but all particles exhibit both wave and particle properties. the correct answer here is all particles show wave-particle duality, not just light. So which formula correctly represents a relationship between the energy E, Planck's constant h, speed of light c, and wavelength lambda of EM radiation? And this is very important, you should know this. The correct relation is C, E is equals to Sc by lambda. This equation is one of the most important in spectroscopy. It links the wave description of light, wavelength and frequency with the particle description, discrete photon energy. So whenever we say a molecule absorbs a photon, we mean it has absorbed exactly this quantized amount of energy. Different wavelengths correspond to different energies and therefore probe different kinds of motion inside molecule. This is the basis of electromagnetic spectrum, which we'll explore next. Let's continue now that we understand light as both as particle and as wave. Let's define it more carefully. Electromagnetic radiation is a form of energy that travels through space as waves. These waves consist of two fields, an electric field and a magnetic field. They oscillate at right angles to each other and both are perpendicular to the direction of travel. That's why we call it electromagnetic radiation. You may notice that in some books the magnetic field is written as H and in others as B. In this course I'll use H, so don't be confused. What's important is that both the electric and magnetic fields are vector quantities, which means that both their intensity and their direction matters. The energy carried by a single quantum of radiation is given by the equation we saw earlier, E is equals to h nu or hc by lambda. This simple relation connects the microscopic quantum world with the observable behavior of waves in space. Let's zoom in the anatomy of the electromagnetic waves, and I'm going to call it EM in short. The wavelength lambda is the distance between successive peaks of the wave, and the frequency nu is how many cycles occur per second. The amplitude is the height of the wave, which relates to its intensity, and the velocity of propagation is always c, the speed of light in a vacuum. Now remember that energy is quantized. High energy radiation has high frequency and short wavelength. Low energy radiation has low frequency and long wavelength. This relationship between lambda, nu, and E is the foundation for why spectroscopy can be used. Here is the electromagnetic spectrum in all its glory. It stretches from long wavelengths and low energies to radio waves and microwaves, all the way to very short wavelengths and very high energies, X-rays and gamma rays. Each region corresponds to a different type of molecular motion or transition. Microwaves probe rotations, infrared radiation probes vibrations, UV and visible light probe electronic transitions, X-ray reveal inner electrons and crystal structures. Think of the electromagnetic spectrum like a grand piano. Each key makes a different note. When we play the right note, a molecule resonates. Spectroscopy is essentially us playing the piano of light to make molecules reveal their secrets. I have repeated from the very beginning that spectroscopy is the study of how radiation interacts with matter. So what actually happens when radiation meets matter? There are three main processes: absorption. The matter takes in energy from radiation. Examples include UV visible absorption, IR spectroscopy, and microwave spectroscopy. Emission. After absorbing energy, matter can release it back as light. This gives us fluorescence, phosphorescence, or X-ray emission. Scattering. The radiation is deflected without being fully absorbed. The key example is Raman spectroscopy, where inelastic scattering tells us about vibrations. Every spectroscopic technique is built on one of these three interactions. Behind all these processes lies one fundamental principle: conservation of energy. We all know energy cannot be created or destroyed. It can only change form. So in spectroscopy, if a photon is absorbed, its energy raises the system from one level to a higher one. When the system relaxes back down, the difference can be released either as another photon or as heat. Mathematically, during absorption, E2 is equals to E1 plus h nu. That means the higher energy level equals the lower energy level plus the photon energy h nu. This balance, this energy in equals energy out, is what makes spectroscopy quantitative and reliable. It's why spectral lines can be treated as precise rulers of molecular structure and dynamics. Now let's bring this all together and connect specific spectroscopic technique to the type of radiation they use and the information they reveal. We have already briefly gone through this, so you can have a look on your own. I have a question now. Why do different substances absorb different wavelengths of light? Think about it. Why do leaves look green? Why does hemoglobin look red? And why does copper sulfate look blue? It all comes down to molecular structure. Each molecule has unique energy levels determined by its atoms, its bonds, and its electronic configuration. And the gaps between those levels decide which wavelength of light can be absorbed. So in the end, every molecule has its own absorption fingerprint, and that's the power of spectroscopy. It lets us recognize substances by their spectral features. Let's look into the energy diagram to understand this. At the lowest energies, we have rotational levels very closely spaced about 0.01 to 10 centimeter inverse. Next comes vibration levels, larger gaps, typically 100 to 4000 centimeter inverse. And finally, electronic levels, much higher in energy, around 10,000 to 50,000 centimeter inverse. Notice the scale. Rotations are fine steps, vibrations are bigger jumps, and electronic transitions are huge leaps. And importantly, all of these levels are quantized. That means molecules can't just have energy, only certain allowed states are there. And the spectroscopy is the art of measuring those steps and transitions. We'll go into each of these in detail as the course continues, but for now, just keep this picture in mind. Now let's make this concrete with an example from nature. Here you see three plant pigments: chlorophyll A, chlorophyll B, and carotenoids. Their structures are slightly different, and that means their electronic energy levels are also slightly different. As a result, each absorbs light at different wavelengths. Chlorophyll A absorbs mainly in the blue and red regions, chlorophyll B shifts a bit, and carotenoids absorb mostly in the blue, leaving the orange color we recognize. The absorption spectrum on the right shows their distinct fingerprints, and that's exactly why leaves change color in autumn. The mix of pigments changes, and so does the light absorption. Now that we understand the principles, let's ask, why is spectroscopy so important? There are three main reasons. Structure determination, it tells us how atoms are connected in molecules. Think of NMR or X-ray diffraction. Compound identification, every spectrum is a molecular fingerprint. With IR or other spectroscopy, we can identify unknown substances. It can be applications, for example, medical imaging like MRI, to environmental monitoring of pollutants, food quality analysis, all rely on spectroscopy. So, spectroscopy isn't just another technique, it's a core tool across science and industries. In the lab, it's essential for structural analysis and quality control. In medicine, it powers imaging and diagnosis from MRI to PET scans. In research, it opens windows into the molecular world, all without destroying the sample. Think of spectroscopy as a stethoscope of chemistry, precise, versatile, and non-invasive. Here's a little thought experiment or a random career question. What do you want to do after graduation? Do you want to work in industry? Do you want to work in academia? Or maybe you want to launch a startup. In all these three cases, you will use spectroscopy. Spectroscopy for product development, quality testing, research, for modern innovations, diagnostic devices. So whatever path you choose, spectroscopy will travel with you It's not just course content, it's a career content. So make sure you understand this. Let me give you some example of few modern applications of spectroscopy. First, food safety. Imagine a handheld sensor that shines near infrared light on your food and instantly reports its chemical composition. This isn't science fiction, it's real. Near IR spectroscopy combined with artificial intelligence can identify contaminants, check ripeness, and even verify authenticity. Of course, there are challenges. Heterogeneous foods often need multiple scans, and not every component can be detected. But even with these limits, this technology is already revolutionizing agriculture and consumer safety. In short, spectroscopy literally helps us to see what we eat. Next, medicine. A startup in New Zealand has developed a UV vis based tool that can measure absorption in turbid or cloudy samples without the distortion caused by light scattering. One powerful application is in quantifying mRNA inside lipid nanoparticles, the exact delivery system used in modern vaccines. Here, spectroscopy provides precise measurements where many other methods fail. It's a perfect example of how fundamental physics supports cutting-edge medicine. Another example, detecting viruses. Surface Enhanced Raman Spectroscopy, or SIRS, uses special substrates to massively amplify Raman signals, even from trace amounts of viral particles. That means we can detect pathogens at extremely low concentrations, and that's critical for early diagnosis and for controlling outbreaks. Here, spectroscopy is not just an analytical method, it's a tool to protect global health. And yes, spectroscopy even enters the courtroom. In forensic science, multimodal imaging with fluorescence and reflectance spectroscopy can reveal hidden traces of materials that are invisible to the naked eye. It doesn't stop at crime scenes. The very same technology is used in art restoration, archaeology, aerospace, and material science. Spectroscopy has truly become a universal language of detection wherever we need to uncover what cannot be seen. So before we finish today's lecture, let's do a last question. Which of the following is not use of spectroscopy? Creating new elements through nuclear fission, identification of compounds, structural determination, medical imaging. The correct answer is creating new elements through nuclear fission. Spectroscopy reveals, it doesn't create anything. So we are now at the end of the first lecture, and let's take a moment to understand what we learned today. We began with history, Newton's prism experiment, Fraunhofer's dark lines, Young's waves, Einstein's photons, and de Broglie's matter waves. From there, we identified three pillars of spectroscopy: wave-particle duality, energy conservation, energy quantization. We defined spectroscopy as interaction of electromagnetic radiation with matter, and we saw how different parts of the spectrum probe different motions, rotations, vibrations, and electronic transitions. Finally, we explored why spectroscopy is not just theory, it's everywhere, in food safety, medicine, virus detection, and forensics. So when you think of spectroscopy, think of it as the science of making the invisible visible. For next lecture, I want to say that we are going to work on fundamentals of spectroscopy part 2. And to prepare, there are a few sections you should review. There are things you have already seen in your earlier courses. You will find these topics in different books. So please take a bit of time to review, and let's meet in our